So in this video, we'll be looking at the second example, where we'll be seeing how probabilistic methods can be used in graph theory. In particular, we'll see that for a graph, there exists a dominating set with small size. So first, let me define what is a dominating set. So a dominating set of an undirected graph G is a set of vertices U such that every vertex that is not in this set U has at least one neighborhood in this set. So let me give you an example. So in this graph, this is a dominating set because you can easily check that all these four vertices have a neighbor that is one of these 2 points. Now let's look at the same graph again. And this time, I claim that this is not a dominating set. And the reason is because this particular vertex here does not have a neighbor that is one of these 2 vertices. So now we're clear with the definition. Let's try to prove the following theorem. So this theorem says that if you have a graph who has n vertices, and then the minimum degree of this graph is greater than 1, which means that every vertex in the graph have at least 2 neighbors. And then we know this graph G will have a dominating set whose size is at most this value here. So the proof idea is the following. So we want to be able to construct a random dominating set, and we want to show that the expected size of this dominating set is at most this value here. So in order to kind of construct a random dominating set, let's first define this random set, so which we call X, and X is a random subset of the vertices, where each vertex is included in the set with probability P. Okay? So of course this is not going to be a dominating set yet, but we'll make it into a dominating set. So as an example, let's go back to this graph here, and let's give each of the vertex a name. And in this case, let's just assume our random set X ended up being BC, which we already argued is not a dominating set. Now let's further define YX to be the set of vertices that is not in X, and also they do not have a neighbor that is in X. So going back to the example we have here, so we know YX will be a subset of this 4 vertices, and we can see that this have a neighbor that is one of BC. Same thing for these 2, and only F is a vertex whose neighbors is not one of BC. So we know in this case YX will equal to vertex F. So lastly, let's define UX to be the disjoint union of X and YX. And just by the definition of YX, you can observe that this random set UX is a dominating set. Now, in order to show this claim we have here, it is enough to show the following. In particular, we want to show the expected value of the size of this random dominating set is less than or equal to exactly this value here. And we want to show that this is true for some value of the probability P, where probability P is a probability whether a vertex is going to be included in the random set X. And the reason that showing this is enough is because this random variable is non-negative. And if you can show the expected value is less than or equal to this is the same as showing that there exists a particular realization that is less than or equal to this value here. So now by the linearity of expectation, we have that the expected size of the dominating set is the sum of the expected size of this random set X plus the expected size of this random set YX. And now let's just work out what exactly are value for these 2 expectations. So the first part is going to simply just be NP, because you have n vertices and each one will be chosen with probability P. Now for the second portion, this will equal to the sum over all the vertices And the summand will be the probability that each vertex will be included in the set Yx. And this can be written down as the following. And now let's work out exactly what is this probability here. So the probability of vertex is not in X equals to 1 minus P. But now we're not simply consider one of the vertices, we also consider its neighbors. So we have to multiply all the probabilities together. So this will become 1 plus the size of the neighbors. And now because we know the minimum degree is delta, so we know this value is going to be greater than or equal to delta. And now we know this quantity will be less than or equal to 1 minus p to the delta plus 1 power. So altogether, we know this expected size of the dominating set is less than or equal to this quantity here. Now let's see how small we can get this value to be. So we want to know at what value of this probability p is this quantity minimized. And this can be done simply just by taking the derivative and set it to be 0. It's really easy to work out. When p equals to this quantity here, this value achieves the minimum, and the minimum value equals to exactly what we want to show. And that will be the end of the proof.